graphics. Yay! Here's a damn. Okay. Mouse is really jerky. You get a list of all threads and the scheduling decisions for those threads. And you see there are different colors used. There's green, which means the thread ran. I can zoom in. Okay. And you see other colors. Oh, this. Yeah, there's orange and there's red. Orange means the thread was preempted. The tooltip shows some information about that period of time which somehow was over. There's red, which means the thread was ready. That is, would like to run, but couldn't run because some other thread ran. I think those are the colors. And this view is quite interesting if you want to get the relation between the different threads. So which thread ran when and which thread was interrupted by which and why this thread to wait for which other thread. This is very nice to see here. And usually the long terms of orange, for instance, are a problem. Or not orange, long ranges of red are a problem because that means that the thread really just wake up and wanted to do something and didn't get the time. So that's something one usually wants to look at. In some cases, it's really just that you have a thread that used a lot of CPU time and other threads didn't get the time. But in some cases, you really have to take this really instant was a problem. Yeah. No. And the final list is a list of all the weight objects. Weight objects are semaphores, condition variables, mutexes, the snooze, conditions, so to speak. Those are listed here. Yeah, for instance, you have a semaphore block cache event, and this object was weighted on 19 times and for a total of 38 seconds. Yeah, interesting information if you want to find out which logs were highly contented, for instance. That helped a lot for the kernel optimizations. That's the main window. There's also a sub window for each thread. You can just select the thread and run it. Let's take this one. Yeah, this is a sub window for the thread, and also the list of weight objects this thread weighted on specifically. And for instance, this is the debugger main thread, application thread. Surprisingly, it weighted a lot on the port reads, obviously for the looper thread. Also on the port disk, whatever that is. That's the kernel, or also kernel automated log. And the final thing you have is a nice graph of the activity of the thread over the time. Also you see the debugger run particularly in that time. It's a runtime display of it. You can also zoom in to see better. And you can also display the other times like preemption and how much the thread was preempted, when it had to wait, how long, and the latencies. Yeah. Overall a very useful tool, but still a bit rough in the interface.
Yeah, that's I think Problem zeigen. Did you want to show the problem of debugger and the analyzing?
But really, you don't see it. It just takes time. That's the only problem. Yeah, I think I should find it. Oh no, I don't ever find the slide. So that's it. Attention, and if you have any questions, now would be the time.
Where are the breakpoints stored with the debugger? Start an application set some breakpoints, and here's the debugger, and we start the breakpoints.
Yeah, it stores the setting on the devices in user settings somewhere.
Ah, okay, then
for this application.
An entry for each application.
Yeah.
There's this variable view in the debugger. It's already, I know that it saved a state at one point, and then this feature got broken by some refactoring. Is it already restoring the variable view, like which ones you collapsed and expanded when you are at the same point in the code again?
I think it works. I think the unrolled it.
You unrolled it, yeah.
Over a year ago.
A year ago.
More than that, probably. That was annoying.
Was that like based on the place in the code that you look at?
Sorry?
Is that based on where you are, on which source file you're looking?
I
think you range.
It's based on what?
It's based on the range of the stack frame.
Yeah.
Since that's of course indirectly associated with the code.
Yeah, nice.
I think once you worked on a B-message value type or something. Is that what was
that works? But basically, you see normally, if you look at a B-message in the debugger, all you would see is just the raw data number. So this does basically preempts that, and it actually tries to analyze the message and show you what values it has in it. So that should actually work. Actually, you put a breakpoint in the message received. If the other message actually has any values in it, then you should. Why is that? Oh wait, because you don't have B in debug mode.
Oh no.
You need debug info for the B.
Okay.
Okay. That's the reason why.
It can only do that for structures that work information for. So if it's a class that comes from a library, you have to have a debug version of that library on it.
I thought you know that this is B message and it just decode the message, but you don't.
Sorry?
I thought you implemented this way that you know that this is a B message type and just decode it as a B message.
I think that actually identifies that actually being short-circuited earlier on because, well, basically it still needs to work information to be able to find the memory locations for it. So, so there's different data numbers it has to pull from, and some of them are dynamically allocated, so it has to be able to look at the addresses for it. So it can't do that without the morph info.
Oh, sorry, I didn't have.
No, it's okay.
How the breakpoints are implemented and how do they live between runs?
Well, they are implemented in browser. There's simply a CPU feature that you can tell the CPU to set a breakpoint somewhere. Also watch point, that's why it's really simple to implement. And whenever the key switches or the current switches on and off the key, then the breakpoints are enabled and disabled for the CPU. And that's basically how it works. These are the hardware breakpoints. Those are limited to 4 implementations. And you can also emulate software breakpoints that work like they go to the location of the code and replace the instruction by an interrupt instruction. And when the code hits this interrupt instruction, it jumps into the kernel and it's emulated like it. Same way.
So if you recompile your executable, you use the breakpoints. Software breakpoints.
No, this replacement of the code is transparent. The application doesn't know anything about it. It's not written to the file, just in memory. And it's dynamically allocated. So sometimes the userland debugger doesn't know anything about whether this is a software breakpoint or a hardware breakpoint. You just request the breakpoint, and the kernel allocates the hardware breakpoints out as it makes sense. So if you just allocated a breakpoint at a certain point, it probably uses the hardware breakpoint if it's available. If it isn't, then it sets a software breakpoint. And when the breakpoint is hit, you have to replace the instruction, obviously, again, for the original instruction, so that the code actually does something. And at that point, it replaces the breakpoint, the software breakpoint, by a hardware breakpoint. So it swaps using software and hardware breakpoints as needed. Yeah. Okay, thank you.